On a clear night, away from the light pollution of cities, the unaided human eye can see several thousand stars. The galaxy contains a few 100 billion individual suns. If only a small fraction of these tiny pinpricks of light had a planetary system, the total number of planets in the galaxy would be enormous. Our local star, the Sun, is a fairly small, calm-mannered, middle-aged star, but its remarkably stable nature might have enabled life to emerge. Astrobiologists are keen to identify similar stars in our neighborhood. Astronomers have identified two nearby stars that closely resemble the Sun. Tau Ceti is the nearest Sun-like star, 12 light-years away, clearly visible to the naked eye. It is twice as old as the Sun, at around 10 billion years, but its planetary disk is about 20 times dustier than our solar system's. This implies a constant bombardment of comets and asteroids could plague the Tau Ceti system. While a guardian gas giant could shield the inner planets from deadly impacts, comet tails and meteorite streaks striking the atmosphere would permanently crisscross the night skies of any Tau Cetian world. Epsilon Eris is smaller, about 80% of the mass of the Sun. Although the Epsilon era has not yet reached its billionth birthday, it is still under intense bombardment. Astronomers will not find any planets within this star's habitable zone, as mega impacts will repeatedly wipe out life before it can establish itself. Such Sun-like stars make up only a few percent of the galaxy, and astrobiologists are desperate to determine which other kinds might be suitable for supporting life within a family of planets. Astronomers classify stars by two basic qualities: their temperature and luminosity. The color of a star's light indicates its surface temperature. Hot stars are white or even blue, whereas cooler stars gleam orange or red. This spectrum divides stars into different classes, each labeled with a letter. Running from hot to cool are O, B, A, F, G, K, and M. Larger stars generally have a higher luminosity because of their size. The Sun is a relatively cool yellow and fairly small, making it a G dwarf. Sirius, the brightest star in the sky, is an A-class giant, and Betelgeuse, the crimson-colored left shoulder of the constellation Orion, is an M-class red supergiant. The HZ is the ring-shaped region around a star where liquid water is stable on a rocky planet's surface. Many factors can affect it, such as the planet's size and its atmosphere's composition, but the basic concept is sound. You can calculate the HZ for any star in the galaxy. Hot stars have a wider HZ and lie further out, whereas cool stars have a much closer HZ. Astrophotography illustrates this relationship, plotting the corresponding stellar class of stable stars, excluding bloated giants, against the star mass and planet positions in our solar system. The HZ around hotter, more massive stars is wider. One would expect these to represent more favorable astrobiological targets. The major problem with hotter stars is that they guzzle hungrily through their nuclear fuel. The most rapidly paced stars last only a few million years, far too short for life to emerge on rocky inner planets. Large stars also violently explode as supernovae, their shockwave shattering any inner planets and char-grilling the moons of gas giants. Thus, the hottest stars, O and B class, are not generally considered capable of supporting life in any potential niches previously described in our solar system. Stars less massive than the Sun present a much more intriguing possibility for astrobiology. The smallest M-class dwarfs are much cooler than the Sun and glow with a dim red light. They are so feeble that even the closest and brightest in our skies, Proxima Centauri, is hundreds of times too faint to see by eye. But such stars are much more numerous than heavier Sun-like ones, so if they could support life on rocky planets, they represent an enormous number of possible oases in the galaxy. They are so thrifty with their fuel resources, sipping through hydrogen-like miserly stellar Scrooges, that no M-class dwarf has ever died. They can last trillions of years. The first ones to form in the early universe are still strong today. This slow and steady routine gives life plenty of time to evolve, so it might seem that red dwarfs are even better than sun-like stars for the prospects of astrobiology. But, unfortunately, they're not ideal nurseries. They present quite a few problems, and astrobiologists are unsure whether these are showstoppers. An M-class star's HZ is about 5 times narrower than that around the Sun. This is quite a small target for rocky planets to form and maintain a stable orbit within billions of years, but there is an even more serious concern about the red dwarf HZ. The shaded stripe represents the region around a star where rocky terrestrial planets can form. Planets do not form less than a certain distance from the star because the dusty material in the solar nebula cannot aggregate. Further out, beyond the snow line of volatile condensation, planetary embryos form from ice and rock, their cores rapidly growing massive enough to sweep up enormous volumes of gas and create giant planets with surfaces unsuitable for life. The dotted line represents the tidal locking limit. If a planet orbits too closely, it gradually loses its rotational momentum to tide the star and becomes tidally locked within a few billion years, always presenting the same face inwards. Mercury is within this threshold and has a locked rotation. Venus is also close and has a greatly retarded rotation, with a single Venusian day lasting 117 Earth days. The entire HZ is within this limit for M-class stars. Any habitable planets become tidally locked relatively quickly. For the very coolest red dwarfs, the majority of the habitable zone falls outside the region of terrestrial planet formation, making life all but impossible. The consequences of tidal locking on a planet orbiting a red dwarf are profound. The planet will perpetually face its star, scorching one side, and never see daylight on the far side. The perpetual sun, looming blood-red in the sky, bakes the facing side dry, while the far side's extreme cold causes the air to freeze and snow down to the arid ground. Between these two extremes, there could be a region circling the world, a twilight zone where the sun hangs eternally on the horizon, where liquid water and perhaps even life itself could exist. To have any real chance of life, a planet fixed by its sun would need a thick atmosphere to redistribute the heat it receives. This would generate a true fearsome wind, as planet-wide convection currents rebalance the temperature gradient, with hot air from the sun side expanding and rushing around to the dark side. However, retaining a thick atmosphere may be difficult for a planet orbiting so close to its star. Mars is thought to have lost most of its original atmosphere, some blown away by the solar wind. Red dwarf planets may be particularly vulnerable, and they must be particularly large to maintain a firm gravitational grip on their atmosphere and have a powerful magnetic field to deflect the solar wind. Furthermore, M-class dwarves have quite an agitated temper. They are much more active in solar flares and sunspots than the Sun, and their brightness can rapidly vary by as much as 10%. Over the past 4 billion years, our Sun has gradually increased brightness by about 25%. The effects of a variable light output are difficult to model, but they are almost certainly very destabilizing for the planetary feedback systems I discussed in Chapter 3. The climate of a red dwarf world could swing between greenhouses and glaciations. Solar flares may be equally problematic for surface life, as UV radiation levels spike enormously every time a solar flare lashes up towards the planet. A thicker ozone shield than the Earth possesses, or other UV filters such as the photochemical haze on Titan, could adequately protect the planet. Another feedback loop may naturally serve to control UV levels. Ozone is produced by UV light splitting apart oxygen molecules, which can be released either by photosynthesis or through the action of UV on water vapor in the air. Therefore, the planet's atmosphere produces more ozone to absorb as the UV levels increase. Even without a complete ozone shield, life around a red dwarf could take refuge underground within fractured rocks, or produce large amounts of biological UV screens, as do terrestrial lichens. Red dwarfs become much more tranquil and cordial as they age. Flares and sunspots are only likely to be a major hazard for the first billion years. After this tumultuous teething period, Earth-sized worlds would still be volcanically active enough to regenerate a thick, insulating atmosphere and have a few 100 billion years of leisure to evolve life. However, the unknown scenario of a tidally locked world orbiting a red dwarf star divides astrobiologists as to whether they represent worthwhile targets. Future searches for potentially life-bearing planets will primarily focus on stars like the Sun. Although the distribution of nearby Sun-like stars has been known for some time, only fairly recently have we been able to address how frequently stars possess a system of planets. Dusty disks have spotted many young stars, but 1991, the first detection of actual planets orbiting another star occurred around a pulsar. Pulsars are a type of star that emits a tight beam of radio waves that sweeps through space as the star rotates, much like a lighthouse's beam. If Earth lies in the path of this beam, astronomers can pick up a rapidly beating signal. Like a celestial metronome, pulsars are some of the most regular objects in the universe. The gravitational tug of an orbiting planet slightly displaces the pulsar's position so that its distance from Earth changes a little. Even though the pulsar is beating at exactly the same rate, the precise timing of the radio pulses varies as the star wobbles. Despite the pulsar's tiny effect, its regular and rapid tick every 6,000ths of a second allows for its detection. This allowed astronomers to infer that two planets of several Earth masses, one much smaller, were in orbit around it. Although pulsars are ideal for planet detection, they are one of the least likely types of stars to find life around. A stellar core collapses into a pulsar after exploding as a supernova. No terrestrial planet could survive this, so the bodies orbiting the pulsar must have reformed from the explosion's shattered debris. These planets will be charred husks of rock, completely sterile. Astrobiologists need other techniques to detect planets around more Sun-like stars. Scientists have discovered 168 planets orbiting alien suns as of this writing, and they are discovering more at an ever quicker pace. The closest one orbits a star just over 10 light-years away from us, and the furthest is 17,000 light-years away. 18 stars possess families of several planets. We can use 4 methods to search for extrasolar planets. The radial velocity technique, the most successful by far, has found around 90% of the known extrasolar planets. An object shifts its light to higher frequencies, blue shifted, as it approaches an observer, and to lower frequencies, red shifted, as it recedes. This is the Doppler effect, commonly described as the characteristic rise and fall in the pitch of an ambulance's siren as it overtakes you. The Doppler shift of a star's light emission provides information about its velocity on Earth. The radial velocity technique looks for a cyclic change in velocity as an orbiting planet gently pulls the star. The magnitude and timing of this effect reveal the planet's mass and orbit that caused it. However, we can only establish a lower limit on the planet's mass due to the unknown angle of the orbital plane concerning Earth. For instance, if the planet's orbit aligns with Earth's line of sight, allowing us to observe the system from an edge-on perspective, even a planet with minimal mass could pull the star towards us at the observed velocity. If the planetary system were more face-on oriented, a more massive planet would be required to produce the measured shift. The transit method detects a periodic dip in a star's apparent brightness as a planet passes and eclipses it. This method only works if the planet's orbit plane lines up with our line of sight, so view the system edge-on. A third scheme, the gravitational microscope, exploits an intriguing aspect of Einstein's theory of relativity. This relies on the fact that a body's gravity can focus an object's light behind it. If astronomers point their telescopes at a region of the sky with many stars, such as towards the center of the galaxy, every now and then, one might slowly brighten and dim as another unseen star passes exactly between Earth and the distant star. Any planet orbits the middle star, and the lens causes its own slight brightening, a blip on the light curve. The fourth method, astrometry, requires extremely precise measurements of a star's position in the sky. As a planet orbits, its gravitational tug causes the star to shift slightly around its center of mass. Theoretically, this wobble in the star's position allows us to calculate the mass and orbit of any planet, but our instruments still need to be accurate enough for this technique to work in practice. Most of these planetary systems aren't much like ours. Jupiter, the Sun's largest planet, orbits at 5.2 times the distance Earth orbits and doesn't even fit on the diagram. But many of these other planetary systems have planets larger than Jupiter in their inner systems. For instance, a newly discovered extrasolar planet, over 4 times more massive than Jupiter, orbits its star, Tau Bootis, at 1/10 of the distance Mercury orbits the Sun. This giant orbits so closely that its year lasts just 3 Earth days, and its atmospheric temperature blisters 1,000 degrees, hot enough to melt the change in your pocket. We refer to these extrasolar planets as hot Jupiters, and their existence remains puzzling. The standard theory of gas giant formation is that the accretion of icy rock small planetary fragments in the outer system allowed these more massive cores to gather heavy atmospheres of gas from the planetary disk. If this model is correct, although it is admittedly based only on the example of our solar system, it means that gas giants cannot form inside the snow line so near their parent star. Hot Jupiters ought to be impossible, but they account for many of the extrasolar planets discovered to date. Perhaps these hot Jupiters didn't form so close to their star, but rather migrated from their birthplaces in the outer system into much tighter orbits. In theory, a gas giant could steadily lose orbital energy as its gravity interacted with the remains of the accretion disk, spiraling in towards the star. This orbital decay is likely disastrous for any inner planets that form, including those fortuitously within the star's habitable zone. The marauding giant's gravitational disturbance would seriously upset their orbits, potentially dragging them into collision, ejecting them out of the system to wander endlessly through the cold void of interstellar space, or plunging them headlong into the star's thermonuclear inferno. The presence of heavier elements in a star's atmosphere proves that its sun swallows planets. The migration ceases once the dust clears the planetary system, ensuring our safety from a Jovian rampage. There are indications, however, that Jupiter did migrate from its birthplace, perhaps 10%, during the early period of the solar system. Even if a gas giant were within the star's habitable zone, its surface would be completely inhospitable. None of the extrasolar planets yet detected could be abodes for life, and, what's more, the hot Jupiters have probably dashed the hopes of any terrestrial planets within the HZ. However, any moons orbiting these gas giants, such as Europa or Titan, transported closer to the Sun's warmth, represent a very intriguing possibility. For these displaced moons to be inhabitable, they must satisfy many of the same requirements as a planet. To give life a fighting chance, the giant would first need to remain stable in the habitable zone for billions of years and, second, not have a very eccentric orbit to minimize climatic swings. Such satellites' energy sources are unlikely to be limiting factors, as they could receive heat from their gas giant's tidal forces from within and from the star above, leading to abundant autotrophy around hydrothermal vents and through photosynthesis. Having formed beyond the snow line and then dragged inwards by its giant's migration, the moon will be brimming with volatile substances, including organic molecules forming the atmosphere and ocean. However, if Jupiter had migrated into the Sun's HZ, it would have melted into a global ocean over 100 kilometers deep. The crushing pressure at the bottom of such an ocean might preclude life around any hydrothermal vents. Although photosynthetic bacteria might happily drift through the surface waters, it is unclear whether prebiotic chemistry could ever produce life under these circumstances. Earth's climatic thermostat, the carbonate-silicate cycle, would also not function on a moon with no land surface. These moons would also become tidally locked to their planet and rotate very slowly relative to the star, presenting similar problems to red dwarf planets. A thick atmosphere could redistribute the uneven heat. But to hold on to this, a moon must be at least 3 times bigger than Ganymede, the largest moon in our solar system. None of these may be critical problems, and life on moons orbiting gas giants remains a fascinating possibility. Indeed, astronomers may already have detected such a suitable gas giant. If you live in the northern hemisphere, step into your backyard on a clear winter night, a summer night in the southern hemisphere, and gaze towards the famous constellation of Orion. Eridanus, the sacred river, runs away from the hunter's outline. Within the fold of the first meander of this celestial stream lies a star with the unassuming name HD 28185. Unfortunately, HD 28185 is too dim to see with the naked eye. This star is a yellow G-dwarf, slightly cooler than our Sun. In 2001, astronomers using the radial velocity technique discovered it has a planet. Despite being 5 times more massive than Jupiter, this world is not believed to harbor life. However, it maintains a circular orbit within its star's habitable zone, with its year lasting only 20 days longer than Earth's, suggesting the possibility of liquid water and life on its orbiting moons. Despite the lack of discovered moons, astronomers consider this system one of the best candidates for alien life. Before the discovery of migrated gas giants, astrobiologists had not even considered the possibility of large moons within the habitable zone. Another eye-opener countered the assumption that planets could only ever form around solitary stars. Our Sun is a singleton, formed simultaneously as other stars within the interstellar cloud, but not gravitationally bound to anything else. However, 2/3 of the stars in the galaxy have at least one companion. The closest star to the Sun, Proxima Centauri, is part of a triple system, orbiting Alpha Centauri A and B, a pair of stars not unlike the Sun. The Sun may be unique in being alone, which could be a critical factor in its habitability. Astronomers have calculated which planetary orbits are stable within a binary star system. For instance, a planet could either closely orbit one of the 2 stars or form a wide circle around both tightly bound stars. However, a figure-of-8 route around both stars is unstable, leading to the eventual expulsion of the planet from the system. However, it was thought impossible for planets to ever form around 2 stars, as their gravitational interplay would sweep the accretion disk away. In 2005, discovering a hot Jupiter within a triple star system was a wonderful surprise, serenely circling its Sun-like parent, while the other pair orbits on an outside path. It is unclear how this unlikely planet could have formed, but it must experience breathtaking sunsets as red, orange, and white suns continually arc through its skies. The most extensive extrasolar planetary family known is that of the star 55 Cancri A. This system boasts one of the smallest planets yet discovered, a Neptune-sized body orbiting close to its star and another 3 gas giants further out. If we discover a 5th planet, we will gain as much knowledge about this entirely alien planetary system as we did about our own solar system during the first 4,000 years of astronomy, with Saturn being the last wandering star. However, the most striking feature of the extrasolar systems discovered so far is how different they are from ours. This is not a lucky quirk of our situation, but rather an artifact of how we search for planets. The techniques described above indirectly detect a planet's presence by its effect on its parent star's light, position, or velocity. Unsurprisingly, our equipment's current sensitivity has only picked up massive planets orbiting very close to their stars. In 1996, the radial velocity technique led to the discovery of Tau Bootis, revealing a corresponding shift of 470 meters per second. Leading research groups are currently achieving a precision of 3 meters per second, the speed of a gentle run, which equates to Saturn's effect on the Sun. This illustrates another important facet of extrasolar planetary detection. Saturn has an orbital period of 30 years, and it takes astronomers at least one cycle to be sure of the mass and orbit of the planet they have discovered. Astronomers haven't been observing for long enough to detect anything besides giants huddling close to their star. However, the design of the next generation of telescopes specifically aims to find terrestrial planets within the habitable zone of their stars. Because of their small size, terrestrial planets are extremely difficult to spot due to their effect on the parent star. Searching for them will require some of the most sensitive telescopes ever built. The turbulence of the Earth's atmosphere would largely swamp any signal from an orbiting habitable world, so most of the next generation of planet-hunting telescopes are to be positioned in space. Launched around 2020, Kepler employs the transit method to identify small rocky planets as they traverse their sun. It will observe 100,000 stars, taking brightness measurements every quarter of an hour for 3 years. Despite the technique's limited ability to identify only line-of-sight planets, it remains optimistic that this sample will identify approximately 50 Earth-like planets. Another project, the Space Interferometry Mission, SIM, will attempt to detect terrestrial worlds by astrometry, as the planet causes the star's position to wobble slightly. This task will require measuring the star's position extremely precisely, as the change in angle to the star is equivalent to the diameter of a cell on Earth viewed from the Moon. SIM will achieve this astounding feat using interferometry. SIM will collect light from the target star using 2 mirrors 9 meters apart. This allows the telescope to emulate having a single, enormous mirror the diameter of that baseline distance, giving SIM the same resolving power but still obviously collecting much less light. Combining the beams from the 2 mirrors causes the light waves to interfere with each other, creating a distinctive interference pattern in which the waves' peaks and troughs either combine or cancel out. This pattern is extremely sensitive to the distance the light has traveled before it enters the mirrors, so as the star wobbles with an orbiting planet, the interference pattern it creates measurably shifts. SIM will use this ingenious technique to check over 2,000 stars from various classes with low precision and focus more closely on 75 of the nearest Sun-like stars. This will provide us with information on the diversity of planetary systems, and we hope to find a few terrestrial worlds within the habitable zone. You can extend this technique to your desired extent, miming colossal telescopes with arrays of smaller collectors. There are several plans for ground-based telescope arrays with up to 200 meter baselines. But if you want a truly enormous array, unhindered by the shimmering and absorption of the atmosphere, you need to be in space. NASA and ESA plan to launch space-based interferometry arrays respectively, the Terrestrial Planet Finder, TPF, and Darwin. These missions will go beyond indirectly detecting a planet and gathering light from an alien Earth. Although the two designs differ slightly in details, they both entail fleets of independent spacecraft, each equipped with its own mirror, positioned along a few hundred-meter baseline, and linked to a hub station for the fusion of light beams. The technological difficulties are astounding. Each telescope craft must point in the same direction and keep its position within the formation to an accuracy of tens of nanometers. Attempting to see an extrasolar planet directly is difficult for 2 reasons. Not only is it very close to the star, but its reflected light is about 1 billion times dimmer and utterly swamped. It's like trying to spot a glowworm crawling around the rim of a searchlight. The trick is to focus not on the visible part of the spectrum, but on the infrared, IR, thermal light. The hotter an object, the higher the frequency of light it emits. The Sun gives off mainly visible light and a little UV, whereas the Earth emits infrared light from its absorbed warmth. By looking for terrestrial planets using infrared, astronomers can decrease this contrast to only 1 million times different. However, in addition to allowing these arrays to emulate an enormous single telescope, interferometry has another trick up its sleeve. We can recombine the beams from the separate mirrors to cancel out the light in the center of the visual field. However, light rays from slightly off-center sources, such as a nearby planet, are unaffected. This allows the telescope to turn down the star's brightness effectively, making the planets stand out. By isolating their light from the glare of the parent star, TPF, and Darwin will detect extrasolar planets, analyzing this dim glow to glean an enormous amount of information about a world. We can determine the length of the days by observing the changes in brightness and frequencies of the light over time. Large areas of water and land contrast with infrared light, revealing the number of continents and oceans as the planet rotates. You can even see desert sand, ice, and cloud cover, which provide a rough idea of the local climate. The planet's orbit may reveal seasonal changes in cloud or ice cover. However, for astrobiologists, the most exciting possibility is to read the chemical composition of the planet's atmosphere. The basic technique of reading chemical composition from transmitted light has existed for over a century. A spectroscope is a device that splits light according to its wavelength, similar to how water droplets produce a rainbow. Different substances emit or absorb light, which produces characteristic patterns in the spectroscope. For example, atomic gases absorb light in the visible region of the spectrum. In 1868, a spectroscope illuminated a solar eclipse, revealing the absorption pattern of a substance never seen on Earth. This new element was named helium, after the Greek helios, the sun. Many molecules absorb infrared light, whose energy levels correspond to different vibration modes in the bonds between atoms. Each type of bond absorbs a specific wavelength of IR, resulting in dips on an infrared spectrum graph where the absorbed light is visible. The appearance of different types of bonds indicates the presence of molecules, and the absorption spectrum represents these molecules. Astronomers can identify the molecules in their atmosphere by spectroscopically analyzing the infrared light collected from an extrasolar planet. In 1999, the transit method covered the extrasolar planet HD 209458b, allowing astronomers to perform visible light spectroscopy on starlight passing through its atmosphere. HD 209458b, one of the most extremely hot Jupiters, orbits so closely to its sun-like star that its atmosphere blasts away into space, trailing behind like a comet's tail. Astronomers have estimated it loses at least 10,000 tons of hydrogen every second. This inflated puff of atmosphere allowed the Hubble Space Telescope to perform spectroscopy as HD 209458b passed in front of its star, revealing the presence of sodium in its absorption fingerprint in the visible part of the spectrum. While this result may not provide much insight, given that sodium is believed to make up only a small portion of the atmosphere and its detection relied solely on its clear spectroscopy signal, it serves as a crucial proof of principle. Once the large space telescopes are operational, we will analyze the composition of alien atmospheres. But what exactly would a planet's air composition represent as a sign of life? How can we determine whether a world light years away is habitable and inhabited? NASA first proposed the idea in the 1960s while attempting to discover potential life on other planets. One proposal proposed using spectroscopy to analyze the atmosphere's chemical composition, a telescope-based experiment that eliminates the need to send equipment to the planet. We expect the atmosphere of an inhabited planet to have deviated significantly from chemical equilibrium. An ecosystem interacts with the planet's rock, water, and air. The very action of life leaves an imprint that betrays its existence. Over the years, this idea has evolved into the Gaia hypothesis, named after the Greek goddess of the earth. Life develops into vast, interconnected webs of species known as ecosystems. Supporting these living networks are the primary producers, extracting energy from the environment to run their metabolisms and reproduction. Different mechanisms of primary production include photosynthesis in surface ecosystems and chemosynthesis in hydrothermal vents or deep basalts. Other organisms, heterotrophs, live off the creative efforts of the producers as herbivores or predators. Sometimes, the two form a mutually symbiotic relationship. like the tube worms and their chemoautotroph companions around black smokers. The most productive ecosystems are densely populated by animals that consume plants, animals that consume other animals, plants that parasitize other plants, and animals that take advantage of the return of nutrients to the air and soil through decomposers like fungi and bacteria. Similar nutrient and energy flow cycles exist in the open oceans and, to a certain extent, in the isolated ecosystems huddled around hydrothermal vents. To paraphrase, no organism is an island in and of itself, but rather a piece of the biosphere, a part of the main. The biosphere is just as dependent on the abiotic components of the Earth. The planet's rocks, oceans, and air endlessly recycle the raw materials of life, carbon, nitrogen, and oxygen. In particular, the atmosphere is a reservoir of resources, such as oxygen for aerobic cells, and a repository for waste products, such as carbon dioxide from respiration. The Gaia theory states that the biotic and abiotic spheres interact, regulate, and balance. Proponents of the Gaia theory describe the Earth as a single superorganism that operates to maintain its stability, thereby stabilizing the entire system. There is no teleological argument here. The Earth does not follow any design. The biotic and abiotic spheres do not intend or strive to balance each other. The Earth is an incredibly complex, interconnected system within which certain feedback loops have spontaneously arisen to control and limit change away from equilibrium. I have already discussed one of these feedback loops in detail. The carbonate-silicate cycle stabilizes the Earth's climate, balancing the opposing forces of rock erosion and carbon dioxide levels. This vital control system now incorporates life. Numerous marine organisms increase the rate of carbon storage by utilizing carbonates to build their shells, which become trapped in limestone deposits upon their demise. Warmer temperatures accelerate the crumbling of rocks on land, while the film of photosynthetic organisms covering the planet fixes carbon dioxide from the atmosphere. Photosynthesis has increased the redox potential of the whole Earth, pumping oxygen into the atmosphere and depositing highly reduced organic matter into ground and sea sediments. Biological processes can have a truly global impact, transforming the conditions and composition of an entire planet. But how can we distinguish between life's action and widespread abiotic chemistry? There is something very special about many of life's processes. The inevitable trend in any system is a decay toward increasing disorder. As distinct from abiotic arrangements of atoms, living things are staggeringly complex and ordered. Only carefully controlled reactions can create such structures, as they cannot arise spontaneously. Life must extract energy from its environment to drive certain reactions, creating complex molecules from simple precursors. Plants, for example, derive energy from sunlight to convert carbon dioxide and water into large carbohydrate molecules like starch, releasing oxygen in the process. Oxygen is very reactive and quickly forms oxidized compounds. So, the oxygen production by photosynthesis indicates these chemical reactions are crucial for life. We say an oxygen-rich atmosphere is out of chemical equilibrium, because we must produce oxygen as quickly as we remove it. One of life's necessary side effects is that it modifies the chemistry of its surroundings in ways that might not otherwise have happened. An oxygen-rich atmosphere is not in itself a positive indicator of life. Several inorganic processes are also known to produce this gas. For instance, the runaway greenhouse effect on Venus would have boiled large amounts of water into the upper atmosphere, whereas solar UV would have split it into two component gases. The light hydrogen would have quickly leaked out of the atmosphere, leaving relatively high oxygen levels. However, high oxygen levels are positive when combined with reducing gases. We must constantly create these reducing gases to keep up with their destruction by oxidation. For instance, the quick oxidation of methane to carbon dioxide and water necessitates the annual production of over 1 billion metric tons to keep the levels in Earth's atmosphere far from chemical equilibrium. Oxygen in the atmosphere is a favorable indicator of water-splitting photosynthesis and may be vital for developing any life more complex than single-celled bacteria. Aerobic respiration releases more energy than any other redox process, except fluorine or chlorine reduction. However, these two gases are too reactive to accumulate in an atmosphere, whereas oxygen is relatively stable. The cells of complex organisms like animals, plants, and fungi consume 10 times more power than prokaryotic cells and require a very rich energy source. An oxygen-laden atmosphere is the only way more complex life could support its power demands. So, if spectroscopic analysis reveals an atmosphere far from chemical equilibrium, such as one with high levels of oxygen and methane, astrobiologists will have a compelling case for suspecting life. Carbon dioxide, water vapor, and methane give beneficial signals to an infrared spectroscope. Their excellent infrared absorption is why such molecules act as effective greenhouse gases. Infrared spectroscopy cannot easily identify atmospheric oxygen, but sunlight's UV converts it into ozone, which is highly absorbent. Nonetheless, the absence of a clear-cut disequilibrium is not necessarily evidence against the presence of life. Although a globally distributed surface ecosystem leaves its signature on the planet's atmosphere, that of less widely established life may remain undetectable. Possible organisms on Mars may have retreated to isolated refuges deep underground. We've detected trace amounts of methane there, but it would be impossible to detect such a slight life signal on extrasolar planets. Even on Earth, detecting atmospheric oxygen would have required 1 billion years of photosynthesis. Scientists have already detected these biosignatures in a planet's atmosphere. In 1990, the Galileo probe swung past the Earth for a gravitational boost to send it en route to Jupiter. As it raced away, it turned its instruments back and measured the reflected sunlight spectrum. Galileo detected the telltale dips, indicating the presence of oxygen and methane in extreme chemical disequilibrium. The probe also saw the absorption fingerprint of chlorophyll, the molecule that captures sunlight during photosynthesis. All these signs, taken together, allowed Galileo's operators to assert, with almost complete conviction, that the Earth harbors life. More recent research has looked at the spectrum of Earthshine, the light coming off the Earth reflected back by the Moon. This diffuse light resembles what we can collect from extrasolar planets and tests analytical skills well. Astronomers could detect the spectral signature of water, ozone, vegetation, and the red cliff in Earthshine. Plants absorb visible light only at a certain frequency and reflect all infrared light to avoid overheating. If our eyes were sensitive to this portion of the spectrum, we would see forests and grasslands in vivid infrared rather than bright green. When viewed on the electromagnetic spectrum, vegetation causes a sudden jump in absorbance beyond the infrared red nicknamed cliff. The frequency at which the red cliff occurs is specific to vegetation's cellular structure. Not all terrestrial land plants produce a cliff simultaneously. Despite some astrobiologists' belief that life across the galaxy could utilize the chlorophyll molecule, which finds its building blocks in interstellar dust clouds, there is no assurance that a similar spectral feature could detect alien forests. Photosynthesis under a red dwarf star would need a leaf structure and chlorophyll-like molecule tuned to lower energy light and able to harness 3 or 4 particles of light to release each electron. Therefore, a universal sign for vegetation would be the observation of any spectral cliff, the magnitude of which waxes and wanes with the seasons on the planet. Looking beyond space telescopes such as TPF and Darwin, astronomers have even more ambitious plans. The baseline distance across the array limits the resolution power of an interferometer, but once we master the technological challenges, we can achieve arbitrarily large arrays. Why settle for a virtual telescope 100 meters in diameter when you could spread your mirrors across hundreds or even thousands of kilometers? Such an enormous array would have a resolution adequate enough to make out features on the surface of a distant terrestrial planet. We could complete this specific project, the Planet Imager, within 30 years. The low-resolution images might look like a pointillist abstraction of dots, but seeing a terrestrial extrasolar planet would be spectacular. We might see a spread of continents, wide oceans, and bright polar ice caps. If the planet had life, we could see desert equatorial regions contrasting against the color of plains and forests. They may even show the same red cliff as our own plant-powered ecologies. We might see seasonal fluctuations in the vegetation on a continent as the hemisphere swings between summer and winter. Imagine if we were to gaze upon the face of an alien Earth just 425 years after Galileo first turned his telescope to the heavens.